Good morning, everybody. My name is John Freilich. I'm an assistant professor in computer science, and I work in HCI. It is my honor to introduce Bjorn Hartmann, who is an associate professor at UC Berkeley, also in HCI, and studies computational fabrication tools, creative design tools for people who make things, programmers. This audience is very diverse, which I was hoping for. I see art faculty here. I see people from machine learning. We have mechanical engineering faculty. And that, I think, helps represent the kind of work that Bjorn does, which spans lots of different disciplines and has implications for a lot of different fields. Bjorn has many different awards. Just to summarize, he's a Colloquium faculty fellow, a Sloan fellow. He has earned both the Akawa and NSF Career Research Awards. And he also co-founded the Citrus Innovation Lab, I don't know, 5, 6, 7 years ago or something? 4 years ago. Which has been a big inspiration to us. He's also the interim faculty director of the Jacobs Institute for Design. With the eRead Center coming, we're thinking a lot about maker spaces and kind of diversifying what computer science is and kind of incorporating more physical computing. So Bjorn has a space that he helped develop where he uses it both for research and teaching. And he teaches a class along with a mechanical engineering professor on some physical computing topics. And I think you'll get that flavor from his talk today. So without further ado, here's Bjorn.
Thank you. So I'm actually not going to talk about VR and AR, but I thought this was a fitting tribute to your major new center that you're going to have coming up on campus very soon. What I do want to talk to you about today is interactive design tools for the maker movement. So over the course of the next hour, I'll show you systems that allow you to take a piece of 3D printed plastic and turn it into an interactive user interface, such as a game controller, by simply adding a camera to it. I'll show you smart circuit construction tools that help you debug your electronic circuits as you build them, as well as some novel machines for making, where you don't just make objects from scratch, but you modify objects that you might already care about, that you may have crafted by hand. Okay, but before we get to those, let's start in the beginning. Who in the audience considers themselves a maker? So not that many. Hopefully this will change with all the new facilities that are coming online. So what is the maker movement? To me, what's really inspiring about the maker movement is that it's this bottom-up effort to engage people from all ages and walks of life in learning how our world of products and electronics, how it works and how it's been constructed, and having them gain hands-on skills to actively participate in that world rather than just be passive consumers of these devices. So take, for example, this electronics workshop in Detroit here, just a few miles from the industrial ruins of decades past, and you get this wide variety of people understanding both the concepts as well as the practical skills of building their own electronics. Now, I live near ground zero of the Maker movement, so this is Maker Faire in San Mateo. The very first Maker Faire, I literally lived across the street and I just walked in, and even at that point there was 20,000 people attending, showing off all their concoctions and projects, and by now it's grown to 150,000 attendees or so in San Mateo alone, and I think 750,000 people who go to maker fairs worldwide. Thought I scraped this off the web and show that there is actually a nice hackerspace right here on campus that of course John was heavily involved in getting it started. And I think there's a trend here that you find at a number of institutions of higher learning that you find these innovation and maker spaces that people are realizing there's something really interesting going on, and it's not just vocational skill. There's a really nice combination of having hands-on skills and hands-on projects drive a pull for conceptual knowledge. All right, so maybe, the maker movement is great. We have all this activity. Is there something bigger at stake here that should make us care about it for research? And I'd like to make a couple of arguments why the maker movement is important and worthy of our attention. The first one, I'll let you read this quote from Bay Area philosopher Alan Watts. Kind of a critique of what our educational system is really focused on delivering. And notice when that was written, that was already back in the 60s. And I think if anything, we've gone further down that road. So, for example, I have seen electrical engineers enter the graduate program at Berkeley, coming from another school, of course, who had never built an actual circuit. They were very strong in the analytical knowledge, but there was a real gap in thinking about how that applied to any real-world situation. Eric von Hippel at MIT makes a second argument for the importance of the maker movement, and that is that a lot of innovations really come from the extreme or power users of a product. So it's often physicians who come up with ideas for improvements to medical devices. It's athletes who come up with ideas for improvements to sports equipment. And if you can give that audience of users better tools, better leverage to actually envision and prototype what a better product could look like, right, then you're increasing the bandwidth of our innovation pipeline. And that is good, and it's very needed, because at the same time we've also had this tremendous export of skills and equipment in manufacturing for decades now away out of the US. So there was this telling article that's now also a couple of years old that Amazon couldn't build a Kindle in the US if it wanted to, because by now it's not just the factories, it's also the supply chains and the expertise that have all moved overseas. And so the maker movement actually is, maybe at small scale, is pushing back against this. So here's an example. This is from our own lab. On the left-hand side is, we bought one of the first 12 3D printers from this company called Type A Machines. They're located in the San Francisco Bay Area. And they had built this entire machine out of pieces from the hardware store and laser-cut plywood. And they sold the first couple dozen printers that way, locally hand-assembled, in order to raise the capital and gain the expertise to then do a redesign that was mass manufactured and looks like a much more robust and polished product. Now, I think our government has taken note of this, and so since 2014, there's been either a White House Maker Fair or a National Maker Fair. We got to send about 10 students from Berkeley last year to the National Maker Fair in DC. It was a fabulous event, bringing groups from all 50 states together. And so there is definitely a realization kind of at the highest level of governments that this is something that's worth paying attention to, because there are really, really positive effects in education, in innovation, and in the sustainability of our own manufacturing infrastructure that can result here. All right, so hopefully I've convinced you that there is something at stake, but there's still the question, does the maker movement need research? Or are they just perfectly self-sufficient and we just let them go and be creative? And well, you can guess what my answer to that question is, otherwise I wouldn't be here giving this talk. But I'll just list a couple of the reasons that I think are really interesting. The first is that making inverts the traditional model of engineering education, right? The traditional model is, welcome, take some math and physics first, then maybe you do signals and systems in EE and maybe assembly in NCS, and then you work your way up to compilers and systems programming, and at the very end, right before you graduate, you get to do a project that puts all of this together. And the Make movement flips this on its head. It says, start with the project you really want to do, and then you'll start floundering at some point, and then you need to look for the right conceptual knowledge that gets you over that hump towards realizing your ideas. What's also motivating to me is that the project makers combine things that we've, at industrial scale, by now separated, right? They combine design, so the exploration of what something should be, together with the fabrication, the actual realization of making it real by forcing atoms in the right shape. Then there's this new digital fabrication tool set. So the kinds of tools you see in makerspaces are not new to industrial manufacturing, but they are new to individual use by non-expert machinists or R&D staff. And I just fundamentally believe also that when you have different user groups, they need different abstractions and affordances in their interfaces. On the one hand, so the users I target tend to be amateurs and designers, so they're different from novices in that there's not always a teaching intent, but they're also different from experts in that you can't assume they have the motivation or the luxury of getting trained for a couple of months on a complex CAD system. So to me, all of these imply a need for new appropriate design tools. And to organize, the way I think about the set of research my group does, it's, I think we're trying to figure out what the 21st century workshop is for makers. And I use the word workshop here very deliberately to tie to some other earlier historical examples. So think about the Wright brothers workshop that allowed them to build a prototype airplane that was controllable. Right? That was their main innovation. It was not that you could do flight, but that someone could actually steer it without crashing. And what enabled them to do that was their background and their tooling as bicycle mechanics and fabricators. So the power tools of the early 20th century. Skip ahead a couple of decades and you get Hewlett-Packard's garage in Palo Alto, which gave rise to information appliances and much of what we see in Silicon Valley, right? And there the tool set was miniaturization of electronics from vacuum tubes to transistors to ICs. And to me, what the 21st Century Workshop is about is a combination of powerful design software that allows users to give specifications at the right level of abstraction for them, combined with digital fabrication tools that give them more leverage, combined with ubiquitous programmable electronics. So design software enables users to create detailed plans, and this is, of course, where a lot of my work as a computer scientist comes in, right? We create the software that lets users create models and plans, whether it's in the mechanical domain, the electrical domain, or the interactive domain. Now, almost every talk by a computer scientist will somewhere have a Moore's Law slide. Here's a different kind of law that doesn't have a name. It's not as fast, but it's maybe just as important. And that is the reduction in price and requirements of CNC software-driven fabrication equipment. So we've dropped by a factor of 1,000 from what would be in a big manufacturing plant to something that you can now have, maybe not yet on your own desktop, but certainly one in your hackerspace or at a local hardware store. And so clearly these desktop fabrication machines are not nearly as powerful as industrial fabrication equipment, but the main shift is they will be used by orders of magnitudes more users for many, many more, for a wider variety of different tasks. And then the last ingredient this is where Moore's law plays out, not in terms of power, but in terms of price plummeting. It's basically free to add computation to it, right? So a Raspberry Pi is now $5 to add a full Linux system in it. If you take an embedded chip, it's maybe 10, 20 cents to add a microcontroller. And so that means that there's really no cost driver anymore that prevents you from adding computation intelligence to your product. So at Berkeley, we've been experimenting with building these 21st century workshops. As John mentioned, the first one was a 1,700 square foot basement. It was the last room that wasn't taken on campus that we could find, that we grew kind of from the ground up. But for about a year now, we've been working in the Jacobs Institute for Design Innovation. So this is a much larger facility now. We have 24,000 square feet over 3.5 floors. And we're really focused on a space that combines making and education and research and have them all intermingle in the same space. So here's just a rough idea of what this looks like. So we have design studios that either fit 50 or 100 students, and then we have an entire floor that is just a makerspace fab lab, and then we have other digital fabrication electronics labs kind of interspersed throughout the space. Here's just an impression of what our makerspace there looks like. It's a beautiful building. I think some of you actually have already toured it. We've had some guests from Maryland, but I certainly invite you, if you're up in Berkeley, to stop by. And here's what one of the classrooms looks like. So very much unlike this room in that everything is on wheels, flexible, can be rearranged, and you can switch back and forth from lecturing, doing conceptual work, to trying something out experimentally on your bench 5 minutes later. Just like the University of Maryland, Berkeley is quite large undergraduate, and so we've gone kind of from zero to operating at scale in just 2 semesters. So we've had 15 different departments teach courses, about 50 different courses we've had through in our first 2 semesters. We train 500 to 600 students every semester on our digital fabrication equipment, and thousands of students have been through the building. And I just want to give you a brief overview of a couple of the types of projects students do in our space. So these are not necessarily research projects per se, but they inform my group's research agenda and that of other faculty members as well. So for example, Daniel Lim worked with a local girl, Sophie, who was born with a hand deformity, to kind of reimagine what a prosthetic can be, from something that you want to hide to something that you really want to show off as, here's my superpower hand. And while maker class 3D printers will not give you the kind of material properties and performance that medical grade prosthetics will give you, it does give you the opportunity to involve your target users in a process of co-creation, and that makes a huge difference in giving someone a feeling of ownership and pride. So this is a mostly mechanical project. We also have lots of projects that basically combine electrical engineering, mechanical engineering, computer science, and user interface design. So here is in California, we're in a multi-year drought, so water conservation is important. Here's a fixture level water flow meter that students designed in a class that I taught. And so the mechanical engineer designed and 3D printed this impeller that is in the pipe, and so it will start spinning when water flows through. It has magnets on its periphery. Outside of the pipe is a copper spool, so you're inducing a current when water rushes through. That current powers up a microcontroller, which then uses a sensor to measure the water flow, and a wireless radio to send that water flow to a user interface that's on a phone. Here's a more whimsical example. This is a energy harvesting rocking chair that, as you rock, generates energy to charge your phone. So what I like about this example, it shows some kind of traditional craft practices, woodworking, welding, being integrated with conceptual knowledge about what's the best way to harvest energy from someone sitting. Well, it turns out suspending a pendulum is more effective than other methods. So then they generated, well, at the pendulum, built the energy harvesting electronics, built a e-ink display into the armrest. We also have a set of medical projects. So Berkeley doesn't have a medical school, but we have a partner university in the U system right across the bay, UC San Francisco. And so often physicians come with great ideas, but there are actually no resources to realize those ideas in a hospital setting. So StepSense was a project aimed at people with sensory ataxia. So, for example, due to diabetes or old age, people can lose feeling in their feet. And if you've ever taken a controls class, if the nerve endings don't send any signal anymore, you're basically walking open loop. And that means you can, the likelihood that you'll slip and fall is much higher. That's, of course, leads to many other medical complications. So this is a very simple idea conceptually. You put pressure sensors into insoles of your shoe and a small wireless radio, and you just relay a footfall signal to cell phone vibration motors that you stick on your back. And your nerve endings still work. And some trials have shown within 10-15 minutes of training, people becoming remarkably more sure in their gait. All right, so this is the variety of projects, and what are some commonalities? Well, there is some mechanical and physical design, right? There's usually some 3D printing, some custom shape. Many of these projects are interactive. There's a user in the loop. And they feature some embedded electronics and a user interface to have that dialogue with the user. So that to me leads then to various different topics of potential research in creating better tools for makers. And so we don't have enough time to go through all of them, so I'll just go through 3 or 4 that showcase a variety of different work we do in our lab. So first I'm going to tell you about some prototyping tools for interactive devices. Our guiding research question there is, how can we make hardware prototyping as fluid as the prototyping of graphical user interfaces? Where we've had decades of tools, going back to HyperCard, that make it very rapid to externalize an idea of how a screen UI could look and what the interaction flow would be. Now, not everything lives as an app on a touch screen, so there are good reasons to build physical user interfaces, especially when questions of virtuosity and performance become involved. Hand and brain co-evolved, and so there's a strong case for leveraging the dexterity and the intelligence we have in our motor system. So all of these types of physical devices, right, abound. And when you look at how these get prototyped, so you walk into a lab like Microsoft Hardware, 3D printers are churning out these form prototypes 24/7. But they only tell you about the form. It's a piece of plastic. It doesn't do anything. And so if you want to make this interactive, well then suddenly things become a lot more complex. Now you have to do electromechanical co-design. You have to do the shape, and then you have to do the interior shape. And where are you going to mount a circuit board? And how are the components on the circuit board going to interact with the outside casing? And so this is the domain of complex CAD authoring software, but this is a high threshold task in terms of expertise. So a first project I want to tell you about was we thought about, well, what about tangible modeling? Is tangible modeling a way of authoring shape intent, and how could we better integrate electronics with things you just sculpt? So we ran an initial formative user study to find out what people are good at and bad at in sculpting, and it turns out they can give you some shape intent, like size and shape, but not everyone is a Michelangelo, right? And so when it comes to complex behavior, like put a joint here, or there has to be a button and it should really be flush with the surface, people tend to draw sketches and annotate them. So it's a sketch plus a sculpted object that is the specification of what it is you want to create. So we took that as inspiration for a system we call Maker's Marks, where you said, what if we gave you modeling, sculpting materials, plus instead of sketching, we'll give you pre-printed paper marks that let you indicate where you want a joint or a hinge to be, or a button or a joystick. And so it should be pretty accessible for users to create these kinds of mock-ups, like of this game controller. Should have this shape, and here's where all the interaction elements should go. And then what if these stickers corresponded to a library of actual physical parts, right? How can we go from this specification to a working game controller that you could use? So our intuition is, we'll start with this as our input, and then we just 3D scan the whole thing. And that 3D scan gives us both the geometry as well as the texture of this object. And then we know we have this library of different marks, the stickers you can place on the object. So we'll basically just run computer vision on all the texture images that our 3D scanner gives us. So we run standard off-the-shelf SIFT algorithms, find these marks in 2D images, and then project them back into the 3D model we've scanned. And then we know at that point we should probably modify this geometry to make a joystick fit. So we have a library of supported parts. Those have associated with them geometry, like it has to be this big, and here's how you would mount it onto a shell. And so that allows us to then automatically process that 3D scan geometry. We shell it, so we make it hollow. We punch through the surface wherever something protrudes, and then we automatically generate all this fascinating geometry. So this means that we need some metadata for each of these components, right? We need the actual components, and then we need various different types of geometric information. How big is it? What does this fascinating geometry actually look like? But if you have that data, then you can just 3D print the resulting process model, and you just snap your pieces into place. So the key idea here is that a maker expresses the shape intent through sculpting, and the functionality intent through these annotations, placing stickers. And the tool then handles all the really tedious, painful geometry modification that has to be very precise. Now, it does rely on this database of metadata about each of the components being available, but we don't actually think that's a big hurdle, because if you're a mechanical engineer, you probably know about McMaster Carr, the biggest source of hardware parts, and pretty much everything they sell already has a CAD model associated with it, because it's a value add for them. If they provide the CAD model, more people will order from them. And so you just need to add a couple of extra bits of information to these CAD models. All right. Now let me tell you about a second approach we took at that same problem. So here we were still using individual PCBs for every single component. And so we thought, well, wouldn't it be nice if we could get rid of that step and allow you to print something on a 3D printer, and then you just add one component, one super sensor to your 3D printed object, and it will just sense all interactions a user would do, for example, with the game controller. So how might that work? So once again, we have 3D print, and then the main idea is, what's a really rich sensor? Well, a camera. So let's take a camera, and we just screw it into the printed prototype, and we do computer vision on the inside of the object. And whenever you push a button, move a joystick, we detect that through computer vision algorithms, and then turn that into high-level interaction events, like for playing a game. So this system is called Sauron, and the idea was pretty simple. Oh, we just add a camera to it, right? But things are rarely ever that simple. So just start from the beginning, though. So we assume someone is creating a 3D model first. and then we'll add to that 3D model a virtual camera that matches all of the parameters of our physical camera. So not just the size, but also the field of view. And then you can basically just, in CAD, we just place the virtual camera inside our object. And now we can run a simulation. Which of the different interaction points are actually visible to that camera? So everything that's green, you're good to go. You can sense that right away. Unfortunately, in any interesting object, probably a whole bunch of the components are not visible. So what do you do about that? So this is where some of the special sauce comes in. So here's the first technique. Camera's in green, field of view of the camera is in blue, and we have this button on the side that's not in the field of view. Well, we're generating this geometry, right? We're in CAD, we haven't fabricated it yet. So we can just change the geometry on the fly. So the simplest technique we could think of is you take that button and you just extrude it until it meets the field of view of the camera. So now, that button, when you press it, will be visible to the camera. And so here, for example, is kind of a complex case for that. We have buttons on all different sides, but we can all extrude them towards to meet the field of view. Now that doesn't always work, so here's another case. Let's say our button is behind a barrier, or it's actually parallel to the optical axis. Then if I just extrude it in the direction of pressing, you're out of luck. So now we want to find some solution, some other solution of making this button visible to a camera. Well, now we'll just use some algorithms from graphics. Specifically, we'll do some ray tracing. So we cast rays from the camera into the scene and reflect them off the boundaries of the object by the surface normal. It's a standard ray tracing algorithm. And then we find rays that eventually intersect our button we want to see. What does that tell us? Well, wherever those rays intersect the boundary, if you just blew a mirror inside, with one bounce, that component will become visible. So one of the themes here is do as many things you can do automatically as possible, but it's totally fine. We're dealing with makers, right? You can also give them some instructions. We can't print specular material yet, but you can just say, hey, at this point, glue in a mirror, and your prototype will work. So then we print the whole modified model, and then comes the highly technical step of improving vision accuracy by improving contrast. So we'll take a Sharpie marker and just mark the ends of all of the different features that we extruded. You can, of course, also use a multi-material, multi-color printer, but that increases the cost of a prototype by a factor of 10 or so. Right? And so then we take the camera, you've seen this, add it in. We also added a ring light, so we add illumination to make sure everything's properly illuminated. And then each component that we know about has an associated vision algorithm associated with it. So, for example, for the slider, we calibrate it by asking the user to just move it through its start and end point. Video here. And so while we could actually calculate what all those positions are, we still add a manual calibration step just to get around imprecisions in how you mount the camera and just general imprecisions of the printing process. So this is simple block tracking, comes pretty much out of the box in any computer vision library. We also do optical flow for some other components. And so we've built game controllers, ergonomic mice, from my own history as a former record label owner as DJs. Of course, we also built a DJ controller hooked up to commercial software. And you might ask, what range of different objects does this support? So we did both an in-person user evaluation where we asked some people with CAD background to model their own DJ controllers. And then we also went online and just downloaded a whole bunch of CAD models and checked whether they're amenable to this technique. And so all of our users were able to, within the allotted time of half an afternoon, to successfully model controllers that could be sensed by our technique. The models we downloaded online, the ones that didn't work, tend to be ones where basically the geometry has thin features where even if you calculate a single bounce, some things will not become visible. So you could, of course, iterate the technique and add more bounces in. But there might also be other parts. Right now we're really just tracking blobs, and you might want to detect how shadows change, so you may not even have to see every component directly. All right, so key ideas here. Use vision sensing on the inside of fabricated objects. And basically what we're doing is turning the standard computer vision problem on its head, right? Standard computer vision is, there's this unknown scene, and we want to create better algorithms to extract information from that unknown scene. Here, we have a completely known scene. In fact, we created the scene. And so we can change the scene to allow us to use standard off-the-shelf vision algorithms. And then kind of the larger idea here is that there's real power in the co-design of geometry and the sensing technique. So you design both together to give you a system with the desired properties. All right, so that was a brief foray into some of the work on prototyping tools. My group is also really interested in learning and debugging tools. So this is work in progress. It's just going to appear in about a month and a half at WIST. So who in the room has breadboarded circuits before? Okay, that is the majority. So breadboards have been around since the 1970s, and were really this amazing step forward in that they radically decreased the time required to build a circuit, and a functional circuit, and test it. However, if you've breadboarded, then you're also familiar with some of the issues. You could call a breadboard a write-only device. Like you build your circuit, and afterwards it's impossible to interpret what it is you built. And so they're also mechanically fragile. So if you were to build a robot with a breadboarded circuit, as soon as that robot bumps into its first wall, some wire is going to pop out somewhere. And then debugging that is quite difficult. So common issues: loose wires, power issues. Where's my power connected? Is it connected? What level of power is connected where? Component polarity. Have I plugged something in the right way or not? Have I plugged my wire into the right pin of an integrated circuit or microcontroller? Is the component working? And so, just as a refresher, this is what a breadboard looks underneath, right? So each row is connected, except not in the middle, so you can place chips in the middle, and then the power rails are connected vertically. So what do you do if a breadboarded circuit doesn't work as intended? Well, you break up the multimeter, right? You measure this point, that point, the other point. Maybe static information is also not enough. Maybe you need information over time, so you break up the oscilloscope, but otherwise it's the same. I'll take my two leads, probe one point, probe another point. So the research idea here is these point measurements actually require you to have a working hypothesis of what the problem is. Now we know from studies of non-expert programmers that they tend to be bad at generating the right hypotheses of what's wrong. And so what we want to do is, let's just get rid of this step of coming up with a single hypothesis to test first. So replace point measurements with ubiquitous instrumentation where we measure everything all the time. And then turn it into an information visualization problem of how to extract useful guidance from all of those measurements. And where this becomes really powerful is if we also have some information about what the circuit is that you're trying to build. So we have some model of even a part of your circuit, right? Then we can combine that model with real-world measurements to diagnose problems automatically. So here's the toast board, or augmented breadboard. So as you build your circuit, you get immediate voltage level information, both on the board itself as well as in the software client. So we'll show you the voltage level on every row. And then you can drag and drop components. So here's what I'm trying to build. And as soon as you do that, then we can do some automated checking as well. So for example, take this LED circuit. If I reverse the LED, we can automatically generate a hint that it's not working because we're not observing the expected forward voltage drop across the diode. Which means you either have reverse polarity or it might be broken. So the idea here is, right, we take some model of the circuit that you express through drag and drop, and then we compare that to the measurements that we observed at that moment. And so we can, that allows us to check, is a component broken? Is something not connected to the right pin? Are we seeing the expected voltages? For example, for an op-amp, have you connected the reference voltage or not? So we can import datasheet information. We can have general knowledge about the characteristics of components. And we can diagnose loose wires. If you don't see the same voltage at both ends of where you tell us the wire is, then you have a connectivity problem. So how is this implemented? So we have a breadboard where we hooked up basically a multiplexer cascade, so we can switch an analog to digital converter to every possible row of the breadboard. We have a microcontroller underneath that just scans through all of these rows. That feeds back information directly on the board, but also to the software client. Pragmatically, how we implemented this is you take a breadboard, you peel back the foam layer, and then you take Z-axis transfer tape, which is this amazing invention, which is tape that only conducts in the Z-axis, but not in the XY axis. So basically, tiny spherical conductive particles suspended in an adhesive. And you just glue it on top of our own custom PCB so we get connectivity to every row. One technical detail then is you can tell when something is as a particular voltage. You can tell by default whether a row is floating, so nothing is connected to it, or whether it's at ground. So we actually have some custom circuitry that if we read a row as 0 volts, we then need to disambiguate whether it's actually connected to ground or whether nothing is connected to it at all. So only for those rows, we then have a second multiplexer where we basically connect it to a pull-up resistor. And if the row is floating, your reading will go up to a very well-specified voltage. If your row is actually grounded, you will still read ground. So we have 2 of those boards working right now, and now the next step clearly in this project is to create about a dozen or so, distribute them in Jacobs Hall, and if that goes well, then we'll take the step of maybe doing 50 or 100 that we can nail out. All right. Going on the home stretch here, so the work keeps getting more and more speculative as time goes on. This is work that's not finished at all yet. Something we're really interested in is exploring the larger space of hybrid fabrication. So what do we mean by hybrid fabrication? Well, think about degrees of automation and intelligence. If I go to Home Depot and I buy a hammer, there's no intelligence in the hammer and no automation. If you take a 3D printer, it's basically all automated and all of the intelligence is in the tool as well, right? You create your STL file and then the machine takes over and you're completely out of the loop. If you buy today's power tools, you get automation and no intelligence. You get a motor on a stick. And so what's in this space in between? We've worked on 2 projects in this area so far. I only have time to tell you about one of them. So we've worked both on augmenting traditional power tools by adding sensing and display and actuation to them, as well as reconfiguring what our automated tools look like. So I'm going to tell you a little bit about CNC Decoration, the project called BanksyBot. And the motivation here is that we observe there's these emerging hybrid art forms where you don't just want to print something from scratch out of plastic or powder, but they're real-world objects that have meaning, aesthetics, and material qualities that digital fabrication alone cannot match. But you can combine digital fabrication with working with existing objects and get to really interesting spaces. And so our first foray in this direction is what we call CNC Decoration. So our idea is to enable makers to modify existing objects with digital fabrication. And for now, we're just working on surface ornamentation, but there's a larger space to be explored. So you start with an object that you maybe handcrafted, or maybe it's a found object, and then we 3D scan that object, and then we allow you to author additional digital enhancements or decorations on that object, and then leave the execution of actually modifying that object to an automatic CNC machine. So you start with an object, maybe something you sculpted, we 3D scan it, and then we show you that 3D model and let you use digital 3D painting applications to draw on it. But we also use that 3D model to automatically generate a mount of that object, so you can insert it into a CNC machine, and the CNC machine will then take over the decoration of that object. So here's a quick demo of what that may look like. So first we scan. And then you end up with that model, and you can start drawing and decorating on it. When we have the geometry, we can also just basically do constructive solid geometry and extrude part of it and then generate a mount that holds that object really securely. Because if you have something arbitrary, right, fixturing itself is kind of a big task in any machining operation. So here we can just generate the fixtures automatically. And then we use these fixtures in a custom modified CNC machine. So here we took an off-the-shelf consumer 3D printer, and we replaced one of the linear axis with a rotary axis. And then we mounted a pen holder onto one of the linear axis, so now the object can spin, and the pen goes on and can draw the object. We've also done this with more industrial strength CNC routers. So you have a router that can move in multiple axes, and we can basically use the same software pipeline with existing hardware as well. Yeah, just wanted to show you. So here's that machine. Here we're not using a pen, but we're using a diamond bit engraver, and this is a sugar skull. And so we can, in this case, actually engrave ornamentation directly on the skull. Now, instead of drawing just in software, there are other modes of authoring as well, right? So we can take what you scanned and print it back out at a different scale. We can print it larger so you can draw on it, scan it back in, extract the marks, and use that to engrave on a small object. So, kind of very much in progress. We've had some successes, and there's also a bunch of work to be done to make this precise and handle a larger variety of different geometries. All right, so those are the projects I wanted to tell you about. Maybe just to wrap up, how do these tools actually help makers? A couple of key themes. Describe goals at a higher level of abstraction and let the tool handle the mapping onto low-level tedious operations. But there's also a distinction between black box abstractions and glass box abstractions. So when you actually don't want the user to worry about something, just abstract it away, hide it in the toolkit. At other times, though, when the complexity is actually inherent in the task, like circuit debugging, gather as much information as possible and show that information to the user. Get more utility out of digital fabrication by intelligently combining automatic and manual processes. So don't be afraid of also auto-generating an instruction sheet that tells a maker what to do manually if you can't do it all automatically. A couple of technical themes here that underlie a bunch of these projects. Take an integrated approach to the mechanical, electrical, and software aspects of these projects, and that's where you can find a lot of value. Right now, the kinds of industry tools that are out there are really siloed in their specific disciplines. And so as soon as you start thinking across disciplines, a lot of interesting gains to be made. Then this co-design of geometry and sensing approaches, right? Combine computer vision or audio sensing or other intelligent techniques with the fact that you're dealing with digital fabrication and you can change the geometry. So I've showed you how to do that with computer vision. We've also done that with audio. So you print geometries that make different sounds that you can then detect with a microphone. For the debugging tools, ubiquitous sensing. Use as much real-world data as you can gather in the process. And then kind of a larger theme is we've been really pushing on integrating 3D scanning as a useful tool in making processes because there are so many pain points right now. Like just scanning and dealing with hundreds of thousands of polygons is just not useful in general. So you have to go higher in the level of abstraction in terms of what the user does with the 3D scanner. Data. All right, a couple of closing thoughts in terms of future outlook. Actually, a lot of the really interesting work in the makerspace right now is driven by material science. So the material science labs are coming up with formulations for workable, durable elastomers, for conductive materials, for multi-material printing, and that's where I think we'll see tremendous opportunities. The mechanisms of the 3D printers, I think, pretty much have ossified in some local minimum, but the materials we're going to use, there's going to be a lot of action there. Now, I was going to tell you, I'm not going to speak about VR and AR, but I do think that these physical construction and debugging tasks are ideally suited for augmented reality. It just might not be a head-worn display, right? To me, the augmented circuit board, the breadboard, that is augmented reality as well. I show you useful digital information in the physical world. And so think broadly about what AR is. And we're definitely using Jacobs Hall as a living lab to deploy and test these tools, and you should do the same here in the human spaces. All right, and of course none of that work was actually done by physically, it was all an incredibly talented set of undergrads and graduate students, so I want to acknowledge all their hard work. Thank you.
So we have some time for questions. Jeff?
So I want to return to your question, your example of the poster board, which I think is a great tool. And you said your goal was to eliminate the need to have people develop a hypothesis and then debug and validate it. But I considered in a university setting that skill and transmitting that skill to students actually be one of our valuable contributions, both job and life. And so if you thought about a way in which you, instead of completely eliminating that, you would use your technology to teach those skills.
Yes, absolutely. So this is actually a great point, and this is a tension that appears in many of these projects. Are you trying to just make some pain point go away, or actually trying to teach conceptual skills? And I've worked across that spectrum. When I build tools for professional designers, I generally just want them to get on with it. But in an educational setting, absolutely. So I think the right way to approach this is you first figure out what the problem is, but then you back off from presenting that solution and instead turn it into a hint that points in the right direction without giving the answer away. So we're doing that, for example, completely other strain of research that I didn't get to talk about today is Jeff in the audience?
Jeff Hopkins?
Yes. So we're on a joint grant program that looks at using program synthesis techniques for helping software developers and also for learning. And so we have a whole tool that we've built that basically takes a student submission to programming exercises, and we use program synthesis to figure out if it's incorrect, what the edit is, to turn that into a correct program, but then we don't show that. Then we back off and say, we figure out, well, is this like a data flow problem or a control flow problem? And based on that, tell you, check about what happens in the third iteration of the loop, or other things that still force you to think through and localize the problem for yourself. So absolutely, yeah. And we could do that for the first word as well.
Other questions? All right, well, thank you for joining us. Thank you for your lecture.